Hello everyone. Hello NPTEL. Can we start the?
Yes, sir. Yes, sir. We can start now.
Okay. So I see two participants here. I see Miss Sandhya and Miss Yashaswini. I will also open the YouTube link. Yeah. Currently there are no participants. Am I right?
Yes, sir.
Okay. So we will just wait for some time.
Okay, sir.
So meanwhile, how many students took this course while we wait for the students?
Uh, Around 1,700, sir.
1,700 students. Okay. And has the general feedback been okay? The assignments, my TAs could conduct all the assignments on time and etc.
That I need to check with office, sir.
Okay. Hello, Tanay. We have one participant here. Okay, hello to all who have joined. Um, so feel free to either write in the chat or even ask your questions here. But more than that, also feel free to give feedback regarding the course. How did you all find the course? Was it helpful? Did it help you in your own learning? Is there anything that you can tell me so that I can improve the course? All this is very appreciated. Okay, I will. Sorry, I'm just seeing the NPTEL message here. So many questions are being posted on the chat. So I'll just make it convenient for everyone. So one question on the chat was, what does the built-in potential of the PN junction diode depend on? And this is pretty straightforward to calculate from the Poisson's equations. Okay, so effectively it depends on the Fermi level positions of the P side and the N side of the junction, which in turn depends on the doping concentration. And when you solve Poisson's equation and you solve for the built-in potential, you'll find that it's if you're looking for an equation, you will get something which is the thermal voltage, which is kT by Q, into the logarithm, the natural logarithm of the product of the dopants, that is Na into Nd divided by Ni square, where Ni is the intrinsic carrier concentration. So just to throw out some typical numbers, let's say KT by Q is about 25 millivolts. It will be slightly more than that at room temperature. So let's say it's about 25 millivolts. Let's say Na and Nd are roughly 10 to the power 16 each. Ni is roughly 10 to the power 10 for silicon, and all this is per cc. Okay, 10 power 10. Ni is the intrinsic carrier concentration at 300 Kelvin, which I'm going to assume is about 10 power 10 per cc. Then the natural log of 10 power 32 by 10 power 20, which is Na Nd by Ni square, is roughly 27. Okay, it's a little more than 27. So that 27 into the thermal voltage, which is 25 millivolts, will give you something like 0.675 volts, which is where this number of zero point 0.7 more or less comes from. Okay. So it's not a fixed number. It's not zero point 0.7 for each and every case. Uh, it is for a typical diode, but it fundamentally depends on the dopant concentrations on your PNN side. So if you change that, your built-in potential changes. Okay, and when you're operating a PN diode in a circuit, you operate well beyond this zero point 0.7 volts, because within that zero point 0.7 volts uh, is when you have moderate forward bias, or let us say your low level injection condition. And well beyond that, you have many other effects that come in. You have high level injection, you have the resistance of the NNP type, the quasi-neutral regions becomes very important. And you also have the contact resistance that becomes important. So all these factors have to be taken into account. Okay, and you have the non-idealities creeping in at this stage. Also, if any of the TAs have not answered any other questions during the course, uh, during the other interactions they've had during in the course, the students are free to email them to me, or even put it out here if they attend the session. Please do reach out if there is any point of confusion. So there is another question regarding the barrier width for the NNP side regions. I'm assuming the student is referring to the depletion region width for a PN diode. And see, once again, the depletion width for the PNN side, it depends on the doping. And, you can use the results obtained from the Poisson's equation along with other conditions. Other than the fact, I mean, along with noting the fact that difference in the Fermi levels is the built-in potential to obtain actual relations for the depletion region widths. In but particularly if your dopant concentration is high, okay, it's a very useful relation to remember, which is the dopant concentration in the depletion width in a certain region is a constant, right? So your Na into Xd in the P region will be equal to Nd into Xd in the N region, where Xd is the depletion width in the N and P region respectively. So if your dopant concentration is high, it means that in a smaller depletion width, you are able to screen all of the electric field, and therefore the depletion width in that region will be smaller, right? So that is something useful to remember. Now, for a long and short PN junction, okay. See for a long PN junction and short PN junction, the fundamental difference is not so much the width, but it's how are you going to place the boundary condition, right? So what matters here is what are you going to be looking at when you're building the IV characteristics or the current voltage characteristics. So one boundary condition that you use for a long diode is that the concentration grade or the excess carrier concentration in forward bias, it becomes zero as you head towards the far end of the diode near the contacts. That is, you go deep into the quasi-neutral regions and towards the contacts, the excess carrier concentration due to the injected carriers becomes zero. Okay, now you cannot make that assumption in a short base diode. Okay, that's the difference. And what is the barrier width for a Schottky barrier? Okay. So since you're talking about the barrier width, I'm again assuming that it's the depletion region width that you're talking about. And once again, you can identify that from solving the Poisson's equation. Okay, there is a relation between the depletion width and the built-in potential. In fact, you'll find that the built-in potential for these diodes, they vary as the depletion width varies as the square root of the built-in potential, because the Poisson's equation under full depletion approximation yields a quadratic relation in space, right? That is, the potential varies as x square. Therefore, the depletion width will vary as the square root of the built-in potential. And the other question is, what is the relationship between the diffusion coefficient and current density? Uh, well, current density implies, I'm assuming you're implying the diffusion current density. Okay, the diffusion current density, see, diffusion is a process where the driving force is the concentration gradient. So the diffusion current density will be proportional to the diffusion coefficient, which is roughly kT mu by Q from the Einstein's relation, where mu being the mobility and Q the charge, and K is the Boltzmann's constant, and T the temperature. So that is the diffusion coefficient. So Q into the diffusion coefficient into the derivative, right? The dN by dx, or the rate of change of charge concentration or the carrier concentration, is the diffusion current density. Okay, so that's the relation between the two. Okay, let me look at the other questions if there are any. Okay. And also this question on how all this is related to the relaxation time. But relaxation time, I'm assuming the student implies the uh, mean collision time or the time between collisions. So the mean collision time affects the mobility, right? Because it is depending on what the effective mass is. If you know the mean collision time, you can effectively identify mobility, which you can also extract. I mean, you can also extract this effective mass from the EK diagram, right? The d square E by dk square parameter of the EK diagram. So relaxation time affects mobility, and mobility is directly connected to the diffusion coefficient through the Einstein relation. It is kT mu by q, with mu being the mobility. So therefore, yes, in some that sense, relaxation time does affect the diffusion current density. Okay, but none of you have told me how did you find the course? Was it helpful? A lot of questions. How many of you found the course to be helpful? Was it useful? Is there anything that I can add or remove from the course? Was it too difficult? Was it easy? Okay, so Sri Lakshmi, you are online here on the Zoom window. So thanks for the feedback. Okay, and do you have any questions from the course? Uh, is there anything um, that was a little vague and that you could not understand? Okay. Okay, if there are no other questions, NPTEL, maybe we can close the meeting.
Yes, sir, we can.
Yeah. Understandable, Sri Lakshmi. Anyway, fine. A chat is fine as well. All right. It's great that the course has been helpful to you.
Can I close the session, sir?
Yeah, I think you can. Yeah. Thanks a lot. Thank you, everyone.
Okay, thank you, sir.
Thank you.